In this particular video, we're going to go over the entire lesson on our probability section, and we get fairly complicated on today's lesson. But I wanted to run through the entire lesson, that way you'd have a chance in case you missed it, or in case you just want to review it. This is we'll go through the entire part of the lesson. The big thing that we need to understand with probability is the basic calculation for probability. We've got events and a sample space. Events are different ways of our desired result occurring. And here's basically the way that I put it in. The number of desired outcomes, what we're looking for, divided by the total possible outcomes. Okay, so if we're reaching into a bag and it's got blue and red, the desired outcome would be whatever color we're wanting, and the possible outcome, total possible, would be all of the colors in there, whatever the total number is of items. Well, let's start with a little bit of review. So here are two problems. I'd like you to do these two problems. Just push pause on the video. Then whenever you get your answer, then you can push play again, and that will allow you to see if you can get the right answer. Go ahead and push pause now. Okay, and here should have been your answer here. Remember, when these are two specific events, so we're going to be multiplying these two together. On this particular one, you're selecting a black marble, then you're going to select a red marble. These are two different events, so because they're two different events, we're actually going to multiply these two together. Same thing on the second one. Hayden is rolling a die and flipping a coin, so two separate events. We're trying to find the probability that both of those will occur, so we're going to multiply those two different probabilities together. Now let's try one. We're going to get into a little bit less review and more into today's lesson. Here's your problem. It says that the probability that a card drawn at random from a standard 52 card deck is either a spade or a heart. Okay, so if we look here, our possible options here, spades and hearts. Okay, spades, there are 13, so our probability of drawing a spade is 13 out of 52. So if the only question were, what's your probability of drawing a spade, it's 13 over 52, which is 1/4. However, it says a spade or a heart, so it can be either a spade or a heart, either one. And so hearts, there are also 13. So we're going to add these two together. Now this is different than our previous example because these are all the same event. We've got 52 cards laying out. We're only going to draw one, but we want it to either be a spade or a heart, one of the two. So we're going to add these two together. And if we add those two together, that gives us 26 out of 52, which reduces down to 1/2. Okay, so now let's try something similar on that. This particular, here we've got two different problems. I want you to go ahead and try these on your own. Kind of a similar process to what we just did. So go ahead and pause the video now. Okay, here are your answers on those. It should have been 2 over 13 or 4/5. If you wrote those as decimals, that's fine for right now. We're just trying to get the practice in is the big thing. Okay, the probability of selecting either a 2 or a king, there are 4 2s and 4 kings. Same theory goes into this one here. We just have to reduce it at the end is the big one. Okay, so now I've got a more challenging one. With this one here, this is talking about a standard deck, so it's still 52 cards. Again, in a standard deck, we're not including the jokers. So 52 cards, and we want either a face card or a diamond. So we've got to think of all the possibilities that there are. So here we have all of the possible face cards. Over here we have all the possible diamonds. So if we count each one of these up, we find out that there are 12 face cards. So the probability of pulling a face card is 12 over 52. Over here, if we count up all the diamonds, we have 13. So the possibility of getting a diamond would be 13 over 52. So if I just asked you one or the other, that's what they would be. Now I'm asking you, it can either be a face card or a diamond. Now we can't just add these two together because if we notice here, we have some duplicates. All of these and these are already marked over here and here. So we're counting them twice, if you will. So then we have to figure out how many duplicates we have and then subtract that from our total because we don't want to double count them. So we're going to subtract 3 over 52 because that's how many duplicates we have. Otherwise we'd count the jack of diamonds twice, the queen of diamonds twice, and the king of diamonds twice, and we don't want to do that. That would give us the wrong answer. So we're going to add up these. 12 plus 13 minus 3 would give me 22 over 52. Again, we have to reduce it down. That would give me 11 over 26. Okay, so we can add up our two total possibilities, but then we're going to have to subtract out the ones in which they are duplicates. All right, so let's try that on this one here. Go ahead and push pause and you try this problem. Now you want to check your answers and make sure that you got the correct answer on these. Again, we are adding up each individual one, then subtracting whatever the duplicates are. Okay, in this case there are two numbers that are even below a 5. We have a 2 and a 4. Those are already counted in our numbers over here, so we don't want to double count them. Let's try another one. Try this one. Push pause now. Here's your answer on this one. This one got a little bit more complicated only because there are so many different types of artists. You're going to have to count all of those up. Okay, and this one is real similar to the one that we just did with the die. Let's try another one now. So try this one, just push pause now. Okay, and here are our answers on these, and again we have some duplicates here that we need to account for. Now this one was a little bit tricky. This was a little bit different. This one asked the probability that Ethan rolls a 3 first, then he rolls an even number. So this is two different events that occur. And because they're two different events, we're going to multiply those two together. Had the question been what's the probability that he rolls a 3 or an even number, then we would add the two. But because it's a 3, then he rolls the die again. So this is two separate events. When it's two separate events, we're going to have to multiply the two probabilities together. Okay, now we want to calculate the number of different ways that we can get 5 different cards out of a deck of 52. And this one's worded just a little bit weird, so I want to clarify just a little bit. When we're trying to calculate the number of different combinations here, it's not just 52 divided by 5, but we're trying to find out how many different hands of 5 can we have from a standard deck of 52 cards. Okay, so what we're going to do is a combination. This will be 52 choose 5. So 52 choose 5, we get almost 2.6 million. Pretty close to it. Almost 2.6 million. Now let's look at this problem. This problem says a 5-card poker hand is drawn from a standard deck. What's the probability that all 5 cards are hearts? So first we're going to, remember our probability is the number desired, what we're looking for, divided by the total number possible. So the number desired, that's our first one. We've got it, and our desired one are 5 cards of all hearts. In order to calculate that, first we're going to have to determine how many hands we can have of just hearts. So how many hearts are there? Well, there are 13 hearts in a standard deck. So we're going to have these 13 hearts. How many different hands of 5 can I get from 13? So we're going to do a 13 choose 5. Okay, so 13 choose 5 gives us 1287. And then what we're going to do is divide that by the total number of possible ways that we can have 5-card hands. And we just calculated that one previously. That was our almost 2.6 million. So now what we're going to do in order to do the probabilities, we're going to divide this one by this one here. Okay, so we're going to take the 1287, that's our desired. We can have 1,287 different ways we can get hearts. Divide that by the total possible ways we can get our hands. Okay, remember that's our probability, the desired divided by the total number possible. So when we do that, that's going to be our 13 choose 5 divided by 52 choose 5. And if you wanted to, you could just type it in your calculator just like that, and that would give you the answer as well. Okay, but that's 1287 divided by almost 2.6 million. Now this one I didn't tell you to round, but we're going to round this one to the nearest 4 decimals. This would be your answer here. Okay, now let's go ahead and try one of these. Here is your problem. Go ahead and push pause now, and then you can work through your problem and come back when you're done. Here are your answers. And again, if you want to, you can just take this, plug this into your calculator. That will be just fine. These are 20 different balls. 4 of them are defective. However, we're only choosing 2 balls at a time. 2 balls are selected at a time. So the top would be a 4 choose 2. The bottom is still 20 balls. That's the total number, 20 choose 2. Okay, and this one was really similar to the one that we just did. The only difference is instead of 5 cards in your hand, you only have 3 cards in your hand. And this one is a face card, so there are only 12 face cards. This is a 12 choose 3 divided by 52 choose 3. This one asks a bag of marbles has 29 marbles. A bag has 29 marbles in it. Okay, and it gives us all these different ones. We have some white ones, some blue ones, some yellow ones. The question says a marble is chosen at random. What's the probability it's not red? Well, we know automatically that the probability that it's a red marble is 2/29. So we can calculate. What we can do is go in here and add up all these. We can add up all the whites, the blues, the yellows, the greens, the pinks, and then divide that by 29, and that would give us our answer. But a quicker way is if we can take this 2 29ths and subtract it. We know there's 29 marbles total, so if we subtract 2, that's going to give us 27. 27 over 29. What that's really doing is we're subtracting the 2 from our 29, which is really just a 1. The maximum we can earn with the probability is 1. So what we're going to do is subtract 1. We're going to go 1 minus this number right here will give us the probability that it's not red. Okay, that's our 29 29ths minus 2. This is, most of you got to this point here, the 27 over 29, and the way that we did that is we took 2 from our total, which was 29. 2 from our total of 29 gave us our 27. And there are 29 possible, so this is 27 29ths. Well, this is going to be an important concept right here, this 1 minus this number here, okay? Similar way is if I were to ask you, if you had a deck of 52 cards in a standard deck, what's the probability you're not going to choose a king? Well, there are 4 kings in a deck, so we're going to go 52 minus 4 gives me 48. 48 over 52 would be our probability that we're not going to get a king. We could have gone 1 minus 48 over, 1 minus 2 over, 1 minus 4 over 52. And that would give us the same thing, 48 over 52. So let's try one now, and I want you to try this 1 minus. Get in the habit of doing that. That's going to make our future problems a lot easier to handle. So go ahead and try these two. Whenever you're done, push pause, or whenever you're done, then you can come back. So push pause now. Here are our 2 answers. And these are both, again, this one is real similar to the one that we just did. We're trying to figure out the probability that it's not blue, and 2 of them are blue. So we just go 1 minus 2 over 20. That would give us our answer. That would be 18 over 20, which is 0.9. Same thing on this one. It's just easier if we can calculate the probability of getting a $half and then subtracting that from 1. That will get us our answer here. And this concept is really just a feeder into what we're about to do now. Now we're going to start to get a little bit more complicated. So here is our question. A jar contains 8 red tiles and 11 blue tiles. 4 tiles are drawn at random from the jar. We want to know the probability that at least 1 tile is red. Okay, at least 1 tile being red, that means 1 tile can be red, 2 tiles can be red, 3 tiles can be red, 4 tiles can, all the way, 4 tiles can be red, okay? Any of those would work just fine. Now, we can calculate the probability of each one of those, but that's a little bit tedious. It's going to take a long time to do that. Instead, what we want to try to do is calculate the opposite. And this says that at least 1 tile is red. So kind of the opposite of at least 1 tile being red would be 0 tiles being red. And if 0 tiles are red, that's the exact same thing as all tiles being blue. And this is a very difficult concept to understand the first time that you're doing it, but hopefully after some practice it will become a little bit easier. So again, basically the probability that 1 or more is red is equal to the probability that is basically the same thing that, or the inverse of that would be that none of the tiles are red, or in other words, all the tiles are blue. So what we can do is figure out the probability that all the tiles are blue, then subtract that from 1, and that will give us our answer here. So let's kind of work on that a little bit. Okay, so we've got 11 tiles here, of which 4 are going to be drawn at a time. So number of ways of selecting 4 blue tiles from 11 here. So this is going to be 11 choose 4. Okay, 11 choose 4. Then we can calculate the probability, the combinations of the total number of tiles drawn. 4 at a time. There are 19 tiles here, 8 plus 11, 19 tiles. We're going to draw 4 of them at a time. So the number of ways of selecting 4 tiles, it's 19 choose 4. So here's how we're going to do this. The probability of selecting only blue tiles, and you can type this into your calculator if you want. This might be a little bit easier. 11 choose 4 divided by 19 choose 4, which is the exact same thing that we've got right here. If you want to take each one of them individually, that's okay. And then we're just going to plug this into our calculator. We find out that the probability of doing that is 0.08514. So this is the probability that all the tiles are blue. But what we're looking for is the probability that at least 1 tile is red. So we're going to take this one and subtract this, the probability that all are blue, from 1. That will give us the exact probability that at least 1 of the tiles is red. So we're going to take that and subtract that from 1 now. 1 minus this number up here. This is where I got this number right here. It's the probability that all of them are blue, will give me the probability that at least one of them is red. So that's the probability that at least one is red. And you're going to need some practice on this, so definitely we're going to give you practice on the next one. So you want to take a second and kind of go through that. Let's try this one. It's the exact same setup, red and blue tile still. And we're going to use the same process that we were doing before. So go ahead and pause it now and start working on that. And then come back whenever you're done. Okay, here's our answer on this one. And again, it is the probability that at least one tile is red. And the opposite of that, if you will, is that none of the tiles are red. Which means if none of the tiles are red, all of the tiles are blue. So we're going to do a 15 choose 6. That's the number of ways that we can get blue tiles. Divided by 25 choose 6. 25 is 15 and 10, 25 total tiles. They give us 0.03. Then we're going to subtract that from 1. That will give us the probability that at least one of the tiles is red. It's a 0.97 probability, so that's pretty good. Okay, now we're going to move on to something just a little touch more complicated. This one says a microchip company inspects 4 microchips out of a batch of 10. If a defective chip is found, the batch is discarded. So that means if one or more defective chip is found, the whole entire batch is discarded. So we're going to use, you can start to kind of hopefully see the correlation between our previous one that we did, when it's at least one of them being a red tile. This one is, if at least one of them is defective, we toss the entire thing. So the batch contains 3 defective chips. What's the probability that the batch will be discarded? Okay, so we have to think about this again. So we're going to calculate the probability of only selecting good microchips. Now the reason why we're going only good microchips is because it says if at least one of these is defective, the entire thing will be thrown out. So we're trying to figure out what the probability it will be discarded. So we're trying to figure out what the probability is that at least one of these is defective. So that's the same thing as the probability, as 1 minus the probability that none of them are defective. Okay, remember, if it's at least one of them defective, that means it's going to be kind of the opposite, if you will, that none of them are defective. So the probability that none of them are defective, and let's see here, how many good microchips do we have? It says we have 10 total microchips, 3 of them are defective. That means we have 7 good ones. So we're going to do a 7 choose 4. 7 choose 4. Again, this is 7 good ones. We have 10 total, 3 of them are defective, 7 good ones, and we're choosing 4 of them at a time. So 7 choose 4 divided by 10 choose 4. 10 because there are 10 total. Okay, so this is probability of all of them being good microchips divided by the combinations of good microchips divided by the total combinations of choosing microchips. Okay, so we can do that number of ways of selecting 4 good microchips from 7, and the number of ways of selecting just 4 microchips. 4 good microchips, this is our 7 choose 4 is 35. The 10 choose 4, that's 210. Okay, so now we just have this. You can just plug this part here into your calculator if you want. That will get you the answer as well. And that's okay, that will work. And again, this is the probability that we're only selecting good microchips, which is not exactly what the question's asking, so we'll address that in just a moment. But if we did that, plug that into your calculator, you'll get 0.167. Okay, but what the question's asking is, what's the probability that the batch will be discarded? In other words, what's the probability that at least one of them is not a good microchip? It's a defective microchip. So the way that we'll calculate that is we'll go 1 minus the probability that all of them are good. Okay, so we're going to subtract this from 1. 1 minus that will give me 0.833. That's rounding to the nearest thousandth. And this is a lot to throw at you, so you may need to rewind just a little bit and watch it again. It's fairly complex. With some practice, it becomes a lot easier. You know, these are not computation-heavy problems. These are really, you've really got to think about them. If you can think about them, then it's just a matter of plugging a couple numbers, a couple combinations into your calculator, and you'll get the answer. Okay, but let's try one now. This one is really similar to the one that we just did. Here's the one that we just did. This one's almost identical to it. I just changed a couple numbers. So go ahead and give this one a try, and then so push pause now, and then when you're ready to come back, go ahead and hit play again. Okay, and this one here is really similar to the one that we just did. There are 15 microchips, and 4 of them are defective. So that means we have 11 good microchips. So it's 11, and this time we're only choosing 3 of them to inspect. So it's 11 choose 3 is our desired outcome for finding the probability of only good microchips. Divided by 15, there are 15 total, 15 choose 3. But that only tells us the probability of getting good microchips, all good microchips. So we're going to need to subtract that from 1. That will tell us the probability of getting at least one bad microchip, one defective one. So then we're going to go 1 minus this, and this will give us our answer right here. You'll need a little bit of practice on these. I recognize this is going to be a very challenging lesson, but hopefully with some practice it won't be as bad in the future.